Fun?
I got it. Yeah, I got it.
So when I tried to tar it, I ran into a problem because I think to create a new file, where did you get, how far did you get with your mic?
I got like
They give you a student discount, so it's always good.
All right. Well, it is 9 o'clock, so I'm gonna get started. If you guys are sitting in the back, because you're on the wait list, go ahead and pick a workstation here, because it looks like if people are late, and they're late. So go ahead and pick a workstation. And what I'll do today is I will take roll, and at the end of the lecture or at the beginning of the lab time, I will go through. Excuse me. I'll go through the wait list and also people who just wrote their name under the wait list, and if they are attending classes today and also last Wednesday, I will give all of these people as slips, because apparently we have enough workstations in the classroom for everybody, because some people are not showing up, well, at least not yet today. So I'm gonna add everybody to this class. If you're on the wait list and you're here today, you'll be added to the class. Okay. Are there any questions about the homework assignments from last week? Yep.
So I'm using a Macintosh.
Okay.
And everything worked all the way up until I tried to tar into a new file. The very last thing we had to do. And I think it's just a different command for Mac. But I scoured the web and I couldn't.
Okay. So you're using Xcode, I guess?
Well, I didn't really have to go into Xcode.
Did you use the virtual machine?
No, all through the terminal. It has
through the terminal?
Yeah, everything is.
Okay, so you have G works okay without installing Xcode.
Yes, sir.
Oh, great.
Yeah.
So that's your solution.
You don't even have to type anything in. You can just click on it and it does everything. It runs it.
G++?
Well, on the Mac.
Yeah.
You don't have to do any command line input until the last thing where you had to create a new file.
Okay. Okay, I see, I got you. Okay. So, but when we start to do homework assignments, actually, having to compile programs,
right,
that will be the real test of, whether you can get G++ or some kind of C++ compiler installed in the environment.
Right.
So that would be the real test. We're going to go through that today. We'll talk about, how to actually write and compile a program today.
Okay.
The lab time today is going to be a demonstration of me working on a program, going through the editing, the linking, and the compiling of a program. So that will be a good test whether your environment is set up to do it or not.
Okay. Well, I was able to do it all through the command line, but I ended up finding out that you could just click on it and it does the same exact thing.
Click on what?
Just click on the file.
It will run it?
And it runs it all, yeah.
Yeah, but when it runs it, where is it? Where's the output going?
Xcode. So I did it through the command line.
Okay.
And it did the exact same thing as if I click on it and
okay.
it opens it to it. But
okay.
where I had trouble was when I tried to type in the
tar command?
CR drive, right. Mm-hmm. It won't create a new file. The test is done.
Okay, I will have to diagnose that problem during the lab time, because right now I kind of need to move on to the lecture portion. But save the questions so that during the lab time I'll be able to take a look at it. Okay. Any other questions? Okay, no other questions. All right. So if there are no other questions, I'm gonna move forward with the lecture. So I'm not sure how much, I cannot remember how much we went through last time. But today, okay, so today, I managed to get the Linux environment up and running. It turned out the problem last week was because this box has 2 Ethernet ports, and Linux was only trying to use the first one to connect to the internet, and that failed because that port was not connected to anything. And today, I was able to get it hooked up, and so the recording will be much better today. The recording, the resolution would be better, and I think the sound will be a little bit better too. So today is good. All right. So last time, I think we started on low-level mechanisms and representation. Is that correct?
I think we finished that whole.
We finished the whole thing?
Yeah.
Okay. Did we finish the base conversion part of it? Okay. Excellent. All right. So we finished the base conversion part, which is down here. Now, base conversion is very important because in this class, unlike your previous class, which only talks about integers as, okay, we can store integers in variables, in this class, we actually want to look at how it is internally represented, how a number is internally represented as a base 2 number. So base conversion becomes kind of important because of that. I just downloaded the text processor here. This is a file that is not really needed. If you don't want to play with this, that's fine. But I'm just going to show you what it is. It's just a zip file. You can do this in Linux or you can do it in Windows. This one does work in both platforms. So when you unzip the zip file, it kind of breaks into several files. They're all under text processor as a folder. There are certain files that you probably know how to open, well, maybe not. The ODS file, by the way, is a open document spreadsheet file, and that one you have to use LibreOffice to open it. Or a later version of Microsoft Office can also open document format. But what I do want to show you is how to open this particular file. This is what I call a LogicSim file. Actually, not how I call it. This is a real thing. LogicSim is something that some of you will probably encounter again and again. This is the home page of LogicSim, and once again, this is not something that you have to do. But if you want to play with it a little bit, that certainly would not hurt either. It's a logical simulator. That's why it has the name of LogicSim. It's a tool that computer scientists or computer science students, computer engineering students in particular, and also electrical engineering students will probably find useful because it's very easy to use and it has a really fantastic online help, online documentation. So if you want to learn how to make circuits out of logic gates and stuff like that, this tool makes it really easy. And this is the tool that I use to make quote-unquote a processor. So at this point, I'm just going to show you what it looks like. So java.jar, and I have that file already downloaded, so it's already here. LogicSim, and then just have to give it the name of my processor. Okay, there we go. And this is kind of related to what we talked about last week, because this picture shows you a very, very simplistic computer. It has certain components connected by all of these lines, and if you're interested, you can definitely just click on those components and find out what they are. The processor is really, in this case, the processor is. I can tell you which part is not the processor. This part, this little part here, that's the only part that is not. Oh, no, I take it back. Yep, that is this little part here. That's the only part that is not a part of the processor. The rest of it is the processor. So that kind of shows you the complexity of the processor. I'm not going to really demonstrate how this works in today's class, but maybe over time, when we do have time, I'll show you a little bit of how this works. It's the simulation of a processor in software, and it is designed using logic gates and some higher level components. It will be very useful in cisp360 assembly language programming because that's the first thing we go through is how do we design a processor? How does it work inside that little chip? So something for you guys to play with if you want to. Certainly not required in this particular class. I also want to announce the ARC Computer Science Club, or otherwise known as the ARC Dev Club. They meet on Tuesdays and Thursdays from noon to about 2 p.m. And the location is room 152, which is, if you just kind of walk down this aisle, it's across from the fountain on the right-hand side. In room 52, section D, which is kind of like the inner classroom. Okay. Danny is still kind of in charge of leading the club, but he is leaving soon. So you might be seeing a new president of that club this semester. I think it's a good club to join, because if you like computer science stuff and you're on your way to transfer or something like that, you will see many other students in the club who are on the same path. Okay, so you guys can exchange information. You'll be able to meet people who are maybe 1 or 2 years ahead of you, and they can give you tips and kind of show you how to get the process running. And if you decide to become an officer, that's also good experience to put on your, not resume, but how do you call that, a piece of your application? When you transfer to a 4-year university, don't you have to fill in an application and tell people who you are and why they should pick? Extracurricular? Is it called do you have to write a personal statement for transfer purposes?
Yeah.
Penalty University.
Okay, so this would be a great item to put onto your personal statement. Is I have been officer of the local computer science club, and I lead activities like these things. So go ahead and give it a chance if you want to. Just kind of pop in and talk to those people. All right. So we're going to start with this one. This is I'm pretty sure this is a slide that we haven't talked about. So we'll go ahead and start with this one. The first part, which is this part here, well, that's a lot of words, but that's nothing new. Okay, all this stuff we have talked about already in the other slide. Okay, in fact, the other slide had pictures of transistors, vacuum tubes, ICs, and so on. So nothing really new here. And this part, is about the processor. Okay, the processor is the focal point of almost all operations because everything has to go through the processor. We have memory, computer memory. We have I/O devices, like hard drives, USB, and so on and so forth. But everything does have to go through the processor in order to go from one place to another or to perform processing or computation. A processor consists of millions of transistors organized into gates, latches, multiplexers, and other constructs. And if you take a look at the processor design in LogicSim, the one thing that I just showed a little bit earlier, you will actually be able to see all the gates, the latches, the multiplexers, and so on and so forth. So those are the high-level constructs made out of transistors. But this class is not about how to design a processor. This class is about how to program, how to write a program in C and C++. So from the programming perspective, the processor is the one thing that executes instructions as specified by the programmer or the developer, basically you in this class. And as such, it has a lot of significance over the other components, the I/O components, the memory, and so on in this discussion. Now when you look at, I don't want to show that picture yet because it's just giving away something that I want to talk about later. A processor can perform various types of operations, but not really a whole lot. So I'm just going to read this part here. A processor natively can access memory. It can read from memory. It can write to memory. It can access your input-output devices. It can access your hard drive, your CD-ROM drive, your USB, and so on and so forth. It can perform calculations. Now, what type of calculations are we talking about? Depends on the processor. If you're talking about a simple processor, the most basic thing it can do is addition and subtraction. That's it, okay? Even multiplication may be missing on some processors. So you have to do multiplication, or you have to program a processor to perform multiplication using addition, subtraction, and comparison, okay? So it's really that simple. It can make simple decisions. So what kind of simple decisions are we talking about? We are talking about simple decisions like, oh, if this thing or this value is 0, go here. If not, continue execution. That type of simple decision. If this number is greater than this number, go to that place to continue execution. If not, continue execution with whatever is next to it. That type of simple decision making. And it can also perform some quote-unquote miscellaneous operations, which is not as important in programming. And each individual instruction or each individual thing that a processor can do is called an instruction. This is basically atomic. From our perspective, it is atomic. In other words, you cannot break an instruction of a processor into smaller units as far as programming is concerned. If you're in the electrical engineering program or a computer engineering program, then you still have some flexibility as far as breaking an instruction down into even smaller components. They're called microcode, but from a programmer's perspective, you cannot, actually specify your own microcode. So this is the lowest level of programming. And each instruction is basically just a really long sequence of bits, zeros and ones. The word bit, B-I-T, which we already understand, we kind of know what it is. One bit is kind of one place. That can be a 0 or a 1, right? But the reason why it is called a bit is because it is a binary digit. The B is from binary, and then the IT is from digit. Are there any questions so far? Okay, nothing so far. And a bit pattern that serves as an instruction is also known as an opcode, an operation code. And you can look at the bit pattern of an opcode as a native language that a processor can natively understand. Okay? All right, so this is what your computer can natively understand. Long strings of zeros and ones, and it can only perform very, very simple operations like adding, subtracting, comparing, continuing execution at a particular place. Those are the simple things that your processor can do. Not quite the same thing that you have learned in cisp360. There's no conditional statement. There are no loops. There are no subroutines. And it can access memory. It can basically write to memory. It can read from memory. But there's no such concept as a variable. No arrays. Okay? No local variables. No parameters. And so on. So now we have a big, huge gap from what you understand about programming from cisp360 or 301 if you come from Sac City, and what a computer natively understands. So before we move forward, I would like to show you a picture, okay? And it's not the picture on this slide. This is a different picture. Altair, that's it. Okay, so we're looking at an Altair 8800 computer. And most of you probably have not seen a computer like this, so I'm going to click on the picture. And okay, this is an Altair computer. The top part is the actual computer. The bottom part is optional equipment, okay, which consists of a drive of some kind. Okay. If you just look at the top, let me see if I can find another picture with just the top right next to it. Yep, go ahead.
What year is this computer from?
That's a good question. If you just click on the wiki page, that will probably tell you. This page is designed in 1974, and it was featured on the cover of Popular Electronics in 1975. So 74 to 75. How long was that ago?
A long time ago.
About what, 40 years? Yeah, exactly 40 years. Okay, if you count the 1975, that's 40 years ago. Okay, but 40 years is really not that long. Okay, if you compare an automobile today to an automobile 40 years ago, well, yeah, I mean, we have a lot of new stuff today, but the basic design of the internal combustion engine really has not changed all that much. Even transmission, if you drive a stick shift, that really has not changed all that much over 40 years. But when you compare this computer with what we call a, like a disposable computer today, there's a lot of changes. Okay, and this particular computer is not really sold to people who just want to get online, check email and stuff like that. It is sold to a few hundred of build-it-yourself kits to hobbyists. And we're surprised when they sold thousands in the first month. So it was way more popular than originally anticipated. Now the surprising factor is not because oh wow, it's a computer, people want it. It has to do with the difficulty of using it in the first place. Okay, so I'm going to show you the other picture that I was talking about, which is this one here. This would be a good picture because that's your entire computer. What are you going to do about it? What do you do with it? How do you write a program into this thing? And some people are thinking, tech maybe has Wi-Fi, right? Or Bluetooth, so I just hook up a little Bluetooth keyboard and a wireless, monitor, and off I go, typing on it, right? Nope, this is it. The back only has a power jack to hook up power. There's nothing else. All right, so we have a whole bunch of LEDs, which is already one step, in the right direction. Instead of using little lamps, it has LEDs, and a whole bunch of switches. That's it. That's your user interface. That's the entire user interface. So how do you write a program into this thing here? Using only the switches, exactly. So in order to program one memory location on this computer, you flip a whole bunch of switches. Okay, 1 0 1 1 0 1 0 1 1 0, and then you specify the address that it has to go to, which is also in binary. So you have a whole bunch of binary switches just to specify the instruction, another bunch of switches to specify the address, and there's one toggle at the end that you just have to press down and then release it. It's called a latch, so it means you'll register this content at that location. Congratulations, you have just programmed one single memory location. Now how much RAM do you have on your phone? 1 gig, which is 1 billion, right? So imagine doing that 1 billion times. Or several hundreds of thousands times, okay? Even that is, it's just obscene, of how much trouble you have to go through to program this thing. Okay, so let's say you have done that, a few hundred times at least, okay? And now your whole program, hopefully, is entered correctly. Because if you miss a bit, nothing is going to warn you and say, I think you got a mistake here, okay? Your program just won't run right. So let's say you got a program in, okay? When it runs, how do you think it is reflecting the output back to you? And once again, remember, there's no Bluetooth or Wi-Fi here. No 4G. The LEDs, right? The LEDs is your only output. So the LEDs will basically go, turn on and turn off to show you the answer to whatever computation that you ask the computer to do. All right. So how do we write a C++ program with this thing? You don't. You do not. It simply does not have the resources to run a program written in C++. Okay? So are there any questions about this? Yep.
Curious, is this computer just designed for people to learn programming, basically, or?
No, it's just a hobbyist kind of thing. People just buy this thing, just so that they can play with, programming.
Wow. Not
really so much to use it for anything practical. It's really just so that, oh, you know what? I have a computer at home.
I see.
And they can show their friends and neighbors and say, look at my computer. I can program it to do this thing. Say, give me a number to add. Oh, make it not too big, And I can, after throwing a lot of switches, you can say, okay, see, I can write the computer I can make my computer, perform addition or, whatever, simple calculation it is capable of doing. Yep.
But are your results, the visuals on that, or they're like it's monitor or something?
Say again?
Is any? I mean, all your responses are on those LEDs.
Are those LEDs? Yep.
No screen or something.
No screens, nothing. There's no VGA port or HDMI port in the back. There's nothing. This is it. You're looking at the whole computer.
Just
Yep.
a question. Is this so supposedly we're gonna write a program with that computer? Is there the language is what it is.
It's called
the
machine code.
Machine code.
Yep. The programming language that you use for this particular computer is called machine code because you have to look up from a big, huge table to understand which binary bit pattern means what. And then you have to kind of write down on a sheet of paper and say, okay, I want the first location to have this instruction. I want the second location to have this instruction, and so on. So you have to pre-plan everything and how you're going to use the RAM or the random access memory on the computer. And if you miss something, if you miscalculate something, it's not forgiving. I mean, it doesn't give you an error message whatsoever. It just does not work. Okay.
So,
Yep, go ahead.
so maybe that's the first thing they used before creating all the programs, right?
Well, it's not the first, but it's the first popular, hobbyist computer. Now, the processor that it used was the Intel 8080 processor. Okay, some people probably read fast enough to catch that part of from the wiki. The 8080 processor is kind of like the granddaddy of the Pentium processor. Okay, so there is a relationship between the 8080 processor and what you have in your modern computer. So what I want to show you at this point is what we call a data sheet of a processor, which will also kind of explain the instructions. And I'm trying, let me see if I can find the instruction set here. There we go. Okay. All right, so this is the instruction set. I'm just going to zoom in a little bit here. All right, there we go. All right, so we have move instruction. This is called the move instruction. To move from a register to memory location, the bit pattern you have to specify is 0, 1, and then 3 bits here, 3 binary digits to specify which register, and then 110 as the other part of the same instruction. And in other words, to program this computer, to write a program to use the Altair 8800, you have to pretty much have this table with you all the time. Because there's no way, well, okay, I cannot remember all of these binary bit patterns corresponding to what they do. So I will have to look up this table from time to time. If you look down, let me see if I can find the actual arithmetic instructions. Okay, so here are the, you can do subtraction, you can do certain types of logical operations, which we'll deal with in this class. Okay. And then you can perform addition, increment, which is just adding 1, decrement, which is subtracting 1. That's pretty much all I can do as far as computation is concerned. There's no multiplication. You have to make multiplication out of these instructions. And everything, and you cannot even type the words. You cannot just type, pop B on the keyboard and program the computer that way. You have to look up the bit pattern here and specify flip up, up, down, 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 up, and that's the instruction. And then you have to specify the address using another bank of switches to specify where that instruction is supposed to go, and that's how you program this computer. But this is a good illustration of what the processor natively understands, which is nothing like what you learned in cisp300 or 301. How many people learned machine language in cisp300 or 301? You did a little bit?
No, I want that to be in cisp300 because I didn't understand the logic of cisp300.
Oh,
It was weird.
okay.
Yeah.
All right. So I'm hoping most of you understand now that programming a processor natively, speaking the native tongue of a processor, is not easy. Yep, go ahead.
Can you still find some of these computers?
You can probably find one in Santa Clara in the Computer Museum. And somebody probably write one of these things as a simulator, and you can probably get it as an app that can run on your phone. But now that you have me interested in this, I'm blaming that on you. Just kidding. Emulator on Android. Okay, well, let's see. Is there one that can run on Android? Yeah, so far I cannot find it. Somebody is talking about porting it to the Android platform, but you can at least get it running in Java. That's this one here is an Altair 8800 emulator in Java. So you can definitely get it running on a PC, running Windows, running Linux, or running Mac OS 10. So it may not run yet, on a mobile platform yet. So if you want to experience, what people have to go through to program these things, you can certainly do it on a regular PC. It's really good as a good illustration for this class. Okay, so nobody wants to program a computer using a whole bunch of switches, right? Okay, so now we have a gap because we understand or we write code in a certain way. Even if in cisp300 or 301 you use pseudocode or Visual Basic or whatever, it is still what we call a high-level programming language. Zeros and ones, like what we just saw, that's not high level at all. Okay, that's really, really low level. So it's time to show this picture here. I'm pretty sure most of you do not know what this is, because you have to be old enough to watch Star Trek: The Next Generation to recognize. I think these were in one of the very first few seasons of Star Trek: The Next Generation. They are from a race called the Binars, okay, which is a play of the name binary. So these are the Binars. So they talk in a binary language that humans cannot understand. Okay, so now we have a problem because we have the processor, which is this guy here, that can talk only in binary. Okay, the output is all in binary, the input is all in binary, the instructions are all in binary. And then on the other hand, we have cisp300, 301, where we talk about high-level programming constructs like loops and conditional statements. So a high-level programming language is intended for humans, and I picked a particular character in a particular movie, as quote-unquote the human, and it's not really a random pick. I specifically picked Dave Bowman from 2001: A Space Odyssey as an example, because what did he have to do in that movie that has to do with computers?
To kill one.
Well, he had to disable HAL 9000, right?
Yeah.
Because HAL 9000 was getting a little bit homicidal, let's just say. Yep. So for people who have not watched that movie, it's actually a pretty good movie. Kind of long, and by today's standard, kind of boring. Certain parts of it is really boring, like the spaceships, going through outer space actually make no sound. Not like in Star Wars where you can hear, the sound of fighters in outer space where it's supposed to be vacuum, right? So anyway, so now the big question is, how do we go from high-level programming language to get the computer, to get the processor to do what it's supposed to do? There are two ways to do it. One way is called interpretation, and the other way is called translation or compiling. Okay, compiling and translation, I would look at those as the same thing. Interpretation is basically on-demand conversion. It is typically used when interaction is expected. Like in a negotiation, an interpreter would basically perform on-demand conversion of whatever the content is. So if you go to any type of summit, okay, where you have, international leaders of, all kinds coming together to talk about stuff, they would usually have, their own interpreter, and they do, on-demand translation, and it's occurring at real time. Okay, so there are programming languages that can do this type of on-demand translation or interpretation. Translation, on the other hand, is a do-it-all type of conversion. It's kind of like having a book that is written in a different language, and you have someone to translate the entire book from one language to another language, and then basically republish the book in the other language. In the context of programming, both approaches are utilized. Some scripting, or most scripting languages, are interpreted. So that would include, most of the scripting languages that we know of today. Perl is kind of old, Python is new, PHP is popular with websites, And basically all forms of BASIC and Lua, which is kind of like an odd little language, but it's used quite a bit in gaming. So that's why I mentioned it. So all of these languages are basically examples of interpreted languages. On the other hand, other languages are compiled. So C and C++ are definitely compiled languages. In other words, you translate everything in one single shot, and the processor basically gets a copy of the instructions, but in the translated version already. And you're not doing translation on demand in this case. Java is interesting because it is very similar to C and C++ in many ways, but it is half compiled and half interpreted. That's because a Java is compiled into bytecode first, but bytecode is interpreted by a Java virtual machine. So it has elements of both interpreted and also compiled languages. So it's kind of interesting, but this is not a Java class, so I'm just going to let you know that Java is kind of more of a hybrid approach. It's not strictly interpreted, it is not strictly compiled. This part talks about how an interpreted language compared to a compiled language. In terms of efficiency, interpreted is much worse. And that's because you are reinterpreting the same statement over and over and over again. So you lose efficiency as a result. Whereas compiled, you just compile once. And once it is compiled, it is in the native language of the processor, and it executes a lot faster that way. Round 2 is about flexibility. C and C++ is not really known for flexibility. In other words, if you want to build a website using C and C++, every time you make changes, you probably have to shut down web services for a little bit of time because you have to recompile the entire program in order to make it work. Okay? But when you use scripting languages like PHP or Python, you can make changes without impacting most of the system. So in terms of flexibility, it goes to interpreted languages. Round 3 is about proprietary software source code protection. In other words, if you do not want to let people know how you wrote a particular program, which one is better? Well, the obvious choice is compiled. Because when a particular program or library or whatever code is compiled, you are only giving people the translated version. And you're not giving out the high-level programming language version of the code. So it would be much more difficult for people to reverse engineer and find out how things were done or specified to begin with. All right. So now this part is focusing on just C++. The first part is you have to write a program. So what I'll do is I'm going to do it now. During the lab time, I'm going to slow down the process and actually show you guys really kind of like step by step how to do it. But right now, I'm just going to do it as a proof of concept. So I'll just make a folder first. I'll just call it test. And the first step is to use an editor to edit a program. I use Vim. You don't have to use Vim. You can use whatever you want. And Vim is nothing more than a really fancy version of Notepad. It's just a text editor. Okay, it's nothing special. So I'm going to write a little program here. I'm not going to explain all the stuff here, so I'm just going to write the code. Okay. So this is a program written in C++, okay, or regular C. You can look at it either way because C++ is a superset or it's an extension of regular C. Almost everything you can do in C, you can do it in C++. Okay, so this program doesn't really do much. Most people look at this code, even if you don't have any prior knowledge of C++, you kind of know that it's just going to print hello world, and that's it, right? Doesn't really do much. But this is a text file. It's nothing more than just a little text file. If you're on a Windows system, you can use Notepad to create a program like this. Okay, it doesn't take anything special. I cannot run this program. at this point because the processor cannot understand what this program is all about. Okay. Let me show you what the bytes look like, with this program. You don't have to do this, I'm just showing you this just so that you know how a text file is represented. The width of the terminal is not set up right, so I'm gonna change that a little bit here. That's better. And just kind of rerun the program. There we go. So this is what we call a binary or hexadecimal dump of the content of a text file. And what we're seeing here is on this side we have the actual text that is represented by the bytes in the file. This pound sign here, which you saw was actually in the source file, is corresponding to 23 in hexadecimal. We'll talk about hexadecimal in a little bit, but this is nothing more than a way to specify the content of a byte. A byte is 8 bits, okay? So we're basically just looking at the representation of a text file. The processor has absolutely no idea of what to do with this content here because it's not specified in the zeros and ones that the processor understands. This is easy for us to read, but to the processor it is completely meaningless. So the first thing we have to do is to compile the program. Now when you compile a program, it is a translation process. So in this case, we use G++ as a command to do it. And then we can supply some switches or some options to this command. I typically specify -G to enable debugging. Okay, we'll talk about debugging in just a little bit too. It's a very useful concept. It's very important when you're writing programs. -C, on the other hand, specifies that we just want to compile the program. We're not going to link it just yet. I'll explain what is linking in just a moment. And then we specify the file that contains the source file. In this case, it's test.cpp. And then we press the Enter key. It will do its work. And now in this folder, I will have 2 files instead of just 1. Test.cpp is what we call the source file, which is a text file that contains the high-level programming language specification. Test.o is what we call an object file. It is kind of the translated version of the content of CPP, but it's not really quite ready to execute just yet. Okay, so I'm going to take a little bit of time to explain why we cannot run the program using test.o. Okay, what is missing in test.o? Okay, let's say you are let's say you're writing a novel. Okay, how many novels have you read that has only one single chapter or no chaptering? It's not divided into smaller chunks. Okay, very few, if any, right? Okay, so why do we have chapters? Why do we have the concept of chapters in textbooks, in novels, and so on and so forth? It has nothing to do with programming.
To help break up the information.
To break up, a long thing or whatever complicated thing into small sections. But why do we want to break it down into chapters?
Sense of accomplishment.
Sense of accomplishment, okay. Anything else?
Because it's
Different topics, like in a textbook.
In the textbook, you have different topics, and you want to group all the stuff related to that topic into one single chapter, because this way it's easier for the reader to find information. Go ahead.
Yeah, I was about to say the same thing. It's easier for you to look up something
Yep.
if it's divided in chapters.
Just imagine, what happens when you have a calculus textbook that has no chaptering. It is just one continuous flow of text from cover to cover. That would make it pretty hard to read, right? I mean, just think about how your professor will tell you, what to read, or what would be the scope of an exam. It would just be from page blah to page blah instead of, okay, this is going to be chapter 5, chapter 6, and chapter 7, right? So the chaptering thing makes it easier for us to organize things, okay? So if that is the case in programming, we also want to use the same concept, okay? Using quote-unquote chapters to separate or to break a large chunk of program into smaller pieces. So it's easier for the programmer to keep track of things and to organize things. Is that making any sense? Okay. And guess what? In programming, each quote-unquote chapter is what we call a source file. So in this case, test.cpp is a source file. But in real programs, you will have multiple source files instead of just one. And it's because of the same reason as why we have multiple chapters in a complicated or long text. Is that making any sense? Okay. How many times have you seen cross-referencing from one chapter to another chapter? Like when you read a textbook of some kind, I'm just using an example here. So let's say in calculus, okay, how many times do you see a cross-reference from one chapter and say, for a review of this particular concept, go to page blah, blah, blah. Fairly often, right? Because the textbook wants you to be able to find the earlier material easily, just so that if you forget what is the concept of limits, for instance, okay, go back to page blah, 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 and it will talk about the concept of what is a limit, what does it mean to take a limit. And it's the same thing with programming. We have references. We can have references from one chapter to another chapter. So whoever is translating just one chapter at a time will just be doing the translation. So for this particular part, I'm going to use another analogy. Okay, I'm going to use Japanese manga as an example. Okay, so the programmer is basically writing in Japanese because a lot of manga, are imported from Japan. So the author, the person who's coming up with the content, was originally using Japanese, which is equivalent to our high-level programming language, or C++ in this case. And that person will give you, the source code, which is basically chapters and chapters and chapters. Is that okay? All right. And the translation process, which is what this command is all about, is translating each chapter individually. So give me one chapter, of a manga, and I'll translate from Japanese to English. Okay. But in that translation process, there might be some cross-referencing. The translator is not responsible to deal with all the cross-referencing. So when you, as a translator, see a cross-reference from one chapter to another chapter, what you're going to do is you'll put a little post-it next to that page and say, oh, on this page, there's a cross-reference to have to go back to a certain other chapter to talk about a certain thing. Okay, you just kind of leave a post-it here, because when you're translating a particular chapter, do you know the page number of other pages, of other chapters? No, you don't, because you don't even know, how other chapters are going to be stacked up against each other, right? Okay, that's why this file, even though it does have binary code that the processor understands, it cannot execute. The processor cannot run it yet, because this is just one chapter of a potentially multi-chapter book. Is that making sense so far? Okay, so it's not quite ready yet. It is translated, but it has cross-referencing that needs to be resolved. So getting back to my notes, I'm just corresponding, the instructions to my notes here. So the next step is to do the linking. Now, when you're linking a program, it really means, putting all the chapters together and resolving all the unresolved references. Okay, so whoever is doing the linking does not need to know Japanese at all. Okay, because by this time it's already fully translated into English. So whoever is doing the linking needs to go look at all the little tabs, all the post-its, and basically say, okay, this needs to resolve and point to the page that talks about this particular character. Okay, let me look up, which chapter. Oh, on this page, a certain character is explained, or this is the first time this character appears. So I go back to the referring page, okay, fill in the blank and say, refer to page blah, blah, blah for the introduction of this character. That's linking. So linking has two main important steps. One is to locate all the chapters and stack them up into a book. And two is to resolve the page numbers of all the cross-referencing. That part is called linking. Are there any questions about linking and how it is different from translating? Translating is going from Japanese to English, but you may have unresolved references in each chapter. Linking is to put all the chapters together into a book and resolve the unresolved references across the chapters. Is that okay so far? Okay. So what I'm going to do here is to do the linking. Now, interestingly, to do the linking, you also use G++, but you give it a different option so that now it switches from the translation duty to the linking duty. You use -O to specify the name of the executable. An executable, as the name implies, is a program that you can actually run. Okay, the processor can take that file and say, okay, I know what to do with it. You can name it anything you want to in Linux. Okay, there's no restriction of what kind of extension you have to use, but typically people just use a regular name with no extension for an executable, but it doesn't have to be like that. If you want to use extension, go ahead. It doesn't really bother the compiler or the linker in this case. And to serve as the input to the linker, you have to specify all the object files. In other words, you're now specifying all the chapters in the book and say, hey, these are the individual chapters of this book. Put it together into one single book. That's what you're saying. So in this case, we have a really simple case. We only have one chapter in this book, so that's the only file I have to specify is test.o, which is the translated version of that chapter. Are we still doing okay so far in with these concepts? It's okay? Okay. So I run the linker, and if I do a ls, which is a list command, it shows me the content of the current working directory. Now we have 3 files. Test is an executable. We can actually run it, and I'll do it next after I explain this. Test.cpp is the first file that we created. It is the source file. It is written in C++. Test.o is an object file. It is the translated version of the CPP file. It contains the machine code and all the other stuff already, but it does contain unresolved references. In this case, it has a function called the printf, and that is the unresolved reference. All right, so let's go ahead and run the program. When you run a program in Linux, if the program is in the current working directory, you have to use // to specify this is an executable in the current working directory. In DOS, you don't have to do that, but in Linux, you have to do it. And the program prints hello world, and that's it. That is all this program is going to do. All right, are we doing okay so far with the whole process of editing a file, compiling it, and linking it, and then finally running it? Is that okay so far? Okay. So that's basically what this particular part is talking about, all the way up to running a program. So we are now done with this part. We can now go to, we have just done this part here. So as far as this section is concerned, getting started, we are done. In today's lab time, I'm going to talk about the lab, quote-unquote, lab activity, Your World Rocks, which is your first, quote-unquote, programming assignment. It really has very little programming involved, okay? You basically just have to follow a few steps and do what I just did a little bit earlier and make sure that you turn in your program the way it is specified and you're done with it. So what I'll do instead is I'm jumping to basic syntax to talk about expressions and operators, which at least, at the beginning seems like a really, really boring chapter because, all we are going to talk about are expressions and operators and variables. Okay. So we'll start with this slide here that talks about what is a type, what is an expression, and what is a simple statement, the simplest statement in C and C++. So we'll focus on the concept of an expression. This is an expression, so is this one. In other words, when we refer to something as an expression, it's typically just a formula that we understand in math classes, okay? That involves the use of operators. Plus is an operator. The symbol, that looks like that is an asterisk here means multiplication. In case that was not explained in cisp360, That's multiplication in C++ and in most other programming languages as well. Are there any questions about what is an expression? I'll use the whiteboard, well, maybe not the whiteboard. Maybe I'll just use my notepad here, mouse pad, to illustrate what is an expression. 6 is an expression, okay? What is the value of this particular expression? 6, exactly. Let's try, 6 plus 9 is an expression, and it has a value of 15, okay? And you can make really long and complicated expressions like 6 plus 9 times 2 plus 3, okay? That's 15 times 5, which is 75. 75 is the value of this expression. So expression is really nothing more than, operators and actual values. And when you evaluate an expression, it always has an answer. It always has a value corresponding to the expression. Are we still doing okay so far with what an expression is? It can be as simple as just a single number, and you can use as many operators as you want if you want to. Multiplication is an operator, addition is an operator, subtraction is an operator, and so on. Okay. Any questions about what an expression is? Okay. Now, when we refer to an expression, we are implicitly saying it is a in-order expression. Now, when I talk about an in-order expression, it means the operator is between the two things that it's supposed to operate on. Are we doing okay so far? Because when you look at 6 plus 9, what are we really doing? We're adding 6 and 9 together. But the specification of the operation, addition, is between the numbers that we are supposed to be adding. And that's why it's called an in-order specification, because the operator is between the two things that it's supposed to operate on. And to most people, this is the only way of doing things, right? Because from elementary school, this is the only thing that we have been taught, is to put the operator between the two things that it's supposed to operate on. So this is just going to be a little bit of time that I'm going to introduce other ways to specify expressions. Not that it is important in C++, but it is important in the long run if you're in computer science. There are ways to specify the same thing using this representation. Plus 6, 9. This is called a prefix notation. In other words, you specify what you're going to do first, and then you specify the actual things that you're going to do on. Okay, so plus 6, 9 is the same thing as 6 plus 9, except you specify, okay, I'm going to do addition. Okay, what are you going to add? Oh, it's 6 and 9. Add those two together, and it'll give you the same value. Okay? So if I'm to re-express this using the prefix notation, then I will use another pair of parentheses to specify 2 plus 3, and then whatever the result of 6 plus 9 is, and whatever the result is 2 plus 3, I want to use those for my multiplication. So the entire expression will be like this. This is the prefix notation of this particular formula. The prefix notation is particularly useful if you use Lisp. Okay, there's a programming language called Lisp, L-I-S-P, which stands for list processing. Okay, it's a really kind of obscure programming language. It's used in AI quite a bit, and also some of the tools that people use. Is anyone here going to civil engineering or mechanical engineering? Okay, so you'll be also using AutoCAD sometimes. Okay, if you use AutoCAD, AutoCAD has a scripting part, and it's Lisp scriptable. So you might have a chance to deal with that. All right, so we have what we call a infix notation. We have what we call a prefix notation. In other words, the in and the pre refers to the location of the operator. Do you think we're missing one? If there's an in, there's a pre, there has to be a post. Okay, a postfix notation, where the operator is after the things that it's supposed to operate on. So using a postfix operation, 6, 9 plus is the postfix notation. In other words, you give someone a number 6, you give that person a number 9, and that person is just holding on to those two numbers, not knowing what to do with it. And then you say, oh, you know what? Just do an addition to whatever I just gave you. So the operation is the last part to specify. Now the cool thing about the postfix notation is you don't need parentheses. If I want to perform the same thing as the infix notation here, I can say 6, 9 plus, which will basically come up with the sum of 6 and 9, which is 15. And then not telling that person what to do with 15, I'm going to say, okay, hold on to another number 2, hold on to another number 3, and then do another plus. Every time I specify plus, that person will look at the most recent two numbers and perform an addition to those two numbers and end up with one single number, with a sum. Okay? So at this point, I will end up with what? 6, 9 plus will give me 15. 2, 3 plus will give me 5. So on my hands, I would have 15 and 5. I don't know what to do with these two numbers until someone tells me, oh, with those two numbers on your hands, do a multiplication. That is the postfix notation. Postfix notation, you can see, does not need the use of parentheses, because just by ordering, where you specify the operator, the plus and the multiplication, you can specify anything that you can specify in the infix notation using the postfix notation with no parentheses. And that is also why early HP calculators do not use the infix notation, because parsing infix notation actually has more complexity. The postfix notation is far easier from the perspective of parsing on the computer. As far as parsing is concerned, it is easier. So who's going to be so crazy to use that postfix notation? Well, okay, I admit I'm one of those. Okay, you can download a calculator on Android. It's called RealCalc. RealCalc, and it has a mode, RealCalc app. And let me show you here. Okay, that's the that's the app that will allow you to kind of play with postfix notation, otherwise known as RPN. Okay, reversed Polish notation. Okay, it's the same thing. Okay, but aside then older engineers who had to deal with this because that's the limitation of their calculators, what else do you think might make use of postfix? Has anyone heard of PostScript? Okay, used in printers. Okay, maybe not PostScript because that's kind of like an older standard. How about PDF? Has anyone heard of PDF? Portable document format. Okay, that one I think everybody should know, right? If you open up a PDF, inside the PDF, it's actually using the postfix notation to specify how to draw something on a raster device. So it is used, okay? Postfix notation is actually used in modern file formats because it is so easy to parse, okay? All right. So that's kind of, this is just something that is in addition to, the main part of this class is just to introduce the concept of infix, prefix, and postfix. Okay, so let me just finish that here. Okay. All right, let's get back to expressions. So if this whole chapter is just talking about expressions, what possibly can we do with expressions? Well, let's take a look at precedence first, and then we're going to go back and talk about why expressions are so important in C and C++. This is actually a hyperlink. It brings you to a Wikipedia webpage, and it just shows you the operator priority. In other words, if I do not use explicit parentheses, how do we perform, in what order are we going to evaluate an expression? So you can see plus and minus has a lower priority compared to multiplication and division. which is consistent with the usual way of interpreting an expression. In other words, if I were to give you something like this, okay, 6 times 9 plus 3, or make it better, like that, okay, 3 plus 6 times 9. Do we multiply first or do we add first?
Multiply.
We multiply first, okay? In other words, the parentheses around the 6 and the 9, or 6 times 9, is implicit. So C++, has its own rules about priority, like, which one should be performed first, and the Wikipedia page, has a list of that. If you think that you might need this, you can print it out and, take it with you, in the exam or so, or whatever. I cannot remember all of this, so I'm not expecting you guys to be able to remember all of this either. So typically what I do in this class is, in case of confusion where it is not clear whether we should go for this operator or the other operator first, I just use extra parentheses to be clear. All right, well, this is cool. I mean, we have just, talked about how to write an expression, but what can we do with operators? It seems like, it's useless, right? Because, this expression will give us a value of 14, right? Because it's 12 plus 2. But what are we going to do with the value of 14? Doesn't seem to be particularly useful just to talk about expressions. The next slide talks about variables and the assignment operator. This is where the fun begins. So we'll first talk about the concept of a variable. In C++, a variable is an object that has a type, a value, and an identifier. Let's go through this part here. What is a type? A type tells us what we can do with it. In other words, can we use this particular value with that particular operator? It gives us certain restrictions. The type gives us that restriction. The value of a variable, obviously, is just really the state of a variable, and it can change over time. And that's why it's called a variable, because it can change. It also has an identifier. A variable has an identifier, which is its name. Because otherwise, how can you say, I want to use that variable, or I want to add this variable to that variable? Well, this and that are definitely not very good names to use as variables. So, you can name those things in different ways. There are different types of variables in C++. At this point, we'll confine ourselves to local variables because that really is what we should be using. We should not be using global variables. In this particular program, this is a program you can actually just type this in, and it doesn't do anything useful at all, except it illustrates how do we declare a local variable. This is the declaration of local variable x. In other words, we're basically saying we are using a variable with an identifier or name of x of a type integer inside the subroutine main. That's basically what this line is saying. Now, obviously, the rest of this program doesn't make use of x at all. It's just declaring a variable and not do anything with it. Why don't we do something with this variable x? Because we haven't talked about the operator that can do something with it. So typically, what do you want to do first with a variable before you start to use it for something useful? Yep, make it, assign a particular value to it first. So that's why in the next segment, we talk about the assignment operator. The assignment operator is a single equal symbol. And what this line is doing is really just to change the value of x to 0. Okay, let's stop here. What is this actually doing? This is the declaration of a local variable, which basically means we're going to allocate the storage for local variable x, and that's it. Okay? What do you think is the value of x prior to the assignment, prior to x equals to 0? Okay, go ahead.
Garbage.
Say again?
Is it garbage?
It is garbage. Very good. Okay, which is another word of saying it is some leftover bit patterns in memory, which also means we don't know what it is. It has a value, we just don't know what it is. So that's why we cannot just say, oh, let's start to use the value of x right away, because we don't know what it is. If you want to use x as a variable and refer to the value of x, you better make sure that you know what the value of x is before you make use of it. So this statement makes sure that the value of x is in fact 0. Okay? Now this program obviously is not very useful, because all we did was to declare a local variable x, change the value of local variable x from unknown to 0, and then we are saying, okay, we're done, go home. Okay, not particularly useful. Let's go ahead and see if we can quote-unquote debug this program. In other words, let's see if we can see the effect of the assignment operator in using the debugger. We'll go ahead and just rewrite that program. So we'll just call it x.cpp, and it's going to do exactly the same thing as what we have here. Int x, x gets 0, and return 0 here. The first step is to compile, which is the translation. So this time we are using -g -c x.cpp to translate the source file into an object file. Now we have the object file x.o. We can use the linker to link the program. -o to specify the name of the output or the executable in this case, and also specify the object files that we have to use as input to create the executable. And now we have x, which is, we have x, which is the executable. And if I just run x all by itself, that's all we're going to get, because it doesn't have any print statement, doesn't do any type of input-output, doesn't do any calculations whatsoever. So how do we know the assignment operator is actually working the way it's supposed to? Well, we use a debugger. GDB is a debugger, and in this class, I will emphasize the use of a debugger in order to debug programs. Okay? And if you say GDBX, it will run the program, but inside what we call a debugger environment. Everything is on the command line. Okay? In the debugger, you can use L to list a program. L stands for list. You can also type out LIST, that works too. So this is the program. And what we can do is to say, I want this program to stop on line 4, okay, just so that I can see what the value of x is before the assignment operation, and then we can single step and then look at the value of x after the assignment operator. To put a breakpoint, in other words, a breakpoint is a construct so that you can run the program up to, but excluding the line, in this case line 4, and it will pause the program. It doesn't stop the program, because stopping means you can no longer continue the execution. It will pause the program to allow you a time to examine the values of variables, among other things. But this is the basic way of debugging the program. Put a breakpoint, and we'll run the program. And now the program has stopped. Now once the program has paused, okay, I shouldn't say stop, but the program has paused, we can now take a look at the value of x. Okay, one thing you can do is to say print x. Okay, when you use print, you can use any expression. Okay, so you can print 13, it will just print 13. If you say print 4 times 5, it gives you 20. So print can take pretty much any expression you can throw at it, but the most important part is you can also refer to variables in your program. So in this case, I'm examining the value of x. Now, it just turns out that x has an initial value of 0, but that's just by coincidence. Okay? It's not necessarily 0, it's just by coincidence x has a value of 0 to begin with. So obviously, if I single step, which means I'm just going to finish line 4, and then I will pause again. Single step means I want to execute just one line, and then I want it to pause again. If I single step, which is just the lowercase s character, it will stop again. Now, in this case, it's not particularly useful because x had a value of 0 already, and I'm not seeing any changes in this case. But this is how you can run a program without using any type of printing or input and you'll still be able to track the execution of a program. All right, so if this is okay, are there any questions about this particular statement? It's an expression, okay? Let's take a look at the next one, which is this one here. Or take a look at this program. This part is now declaring two local variables, x and y. So now we have two local variables. And the next statement has two assignments on the same line, x equals y equals to 0. So the question is, what is it going to do? The explanation is down here. As it turns out, assignment is not a statement, it is what we call, it's an expression. So as an expression, it returns a particular value. So here, we basically look at this expression here, which is what we have here, and we basically say it's the same thing as this. In other words, you can put parentheses to the right-hand side, and it's the same thing as first evaluating y equals 0, and then the return value, or the value of that expression y equals 0, is used to change x. Okay, is that part okay? Okay, but that's kind of confusing because this thing here, okay, if you just look at the highlighted portion here, y equals 0 in parentheses, is actually doing two things instead of one. The first thing it does is to change the value of variable y to 0. That's the first thing that it does. But the second thing it does is to produce a value of whatever y ends up with, which is also 0. It's the second thing, which is the value of the expression, that we use to change x, because x equals to blah 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 means we have to first evaluate this expression. Whatever value of this expression is, we use that to change x. So this is why, in one single expression, we can now change the value of two variables. Let's go ahead and change our program to test this. Okay, so we'll go ahead and change our program. Oops. .cpp to have one more variable y here, and we'll go ahead and make this a little bit more fun. Okay. So we'll make x equal to 5 first, and then we'll say y equals to x equals to x plus 1 plus 1 plus 10. Okay, so here we have a slightly more involved example of how to use the assignment operator. Before we run the program in the debugger, which is easy, we want to first find out, or at least have a theory of what is the value of x and y by the time we get to line 6. And then we'll use the debugger as a verification of, okay, I think our understanding is correct. Okay. Line 4 is easy. Okay, we are just changing the value of x to 5. So by the time we get to line 5, at the beginning of executing line 5, x starts with the value of 5. Okay? And the first part we have to evaluate on line 5 is whatever is in parentheses, right? So this is the first part we have to evaluate. What do you think is the result of evaluating this particular expression? X becomes 6, right? But that's only the first part of an assignment operator. The second thing the operator is going to do is to specify a value of this entire expression. What is the value of that entire expression? 6. And then we have 6 plus 10, which is 16. And what do we do with 16, which is the entire right-hand side of line 5? What are we going to do with this 16 here? We use it to change y. So y should end up with a value of 16. X should end up with a value of 6. Okay? We are changing the value of x inside the expression that eventually will change the value of y. Now that is something that your CISP 300 or 301 probably did not introduce. Okay? let's check whether that is what the program is going to do. Remember, we have to compile first, so -g-c x.cpp, then we link the program, and then we use GDB to debug the program. We list the program, we'll put a breakpoint on line 4, just like last time, which is the beginning of the entire useful part of the program. We run the program, it now pauses on line 4, and we say print x. Let's take a look at the value of x before line 4. This time it is meaningful because before line 4 executes, x has a value of 5. We single step, which means we execute just line 4 and then we'll pause again. So we are just about to execute line 5, but before we do that, I want to examine the value of x. X now has a value of 5, which is predictable, okay? Are there any questions up to this point? The program is still doing what it's supposed to. Now, the next thing we're going to do is to single step. If you want to, you can print y2. Y definitely has some gibberish in it, okay? Nobody specified this value in y. It's because the declaration of a variable does not initialize it. It just says, okay, allocate the storage for variable y, but it can have any type of bits, the zeros and ones in it. Okay, so we single step line 5 at this point. After that, we print the value of x. We think that x should have a value of 6 at this point, and it does. And we think y should have a value of 16 at this point, and it does have that too. Okay? So we are running out of time as far as the lecture is concerned. There is a quiz that has opened up already. So we'll just kind of go to the quiz here. Oh, no, okay, I'm going to open this up. It's quote unquote a quiz, but it's not really a quiz because you have an entire week to work on it. You can open it, you can think about it. Okay, I take it back. I don't have enough questions yet in the quiz, so I'm not going to open it just yet. I will open it on Wednesday, and then on Wednesday you have 1 week to work on it. Okay, so that's going to be your next kind of like homework assignment. It's not going to be a quiz in the sense that you don't have a limitation of how much time you have to finish it. You can take the entire week from this Wednesday to Wednesday next week up to 9 o'clock to finish it. So from that perspective, it is not like a real quiz where time is limited. All right, so for the lab today, I'm going to go through, it's in the previous section. Okay, in today's lab, I'm going to kind of show you how to do the homework assignment for Your World Rocks. Okay, so you can read the description ahead of time. And we'll take a break for about 10 minutes. We'll come back here at 10:30, and I'll restart the recorder at that time.